Hello, this is Tripoli 41, Lecture 10 on PN junction IV characteristics. Okay, so in our last lecture, we showed what the plot of the charge density, the electric field, and the electrostatic potential or voltage as a function of x in our PN step junction, but under thermal equilibrium values. For this lecture, we'll do the same, but this time with an applied voltage and continue the analysis until we are able to derive the IV characteristics of the diode and show that it follows the form of the Shockley equation. We'll do some approximations along the way and assumptions, and one of those critical assumptions is based on the law of the junction, which gives us the carrier concentrations on the depletion edges to help us get an idea on the boundary conditions for our MCDE. We'll also interpret qualitatively the EBD of a PN step junction under an applied voltage and relate how or visualize how it relates to the expected currents, and also will plot the carrier concentrations on the quasi-neutral regions based on biasing. So how does the carrier concentrations change within the material? Although we'll only do that for the quasi-neutral region and not within the depletion region. Okay, let's have some review or practice first. This time we'll consider a linearly graded junction where the doping profile changes linearly within the device. Again, we're using ND minus NA. So when ND minus NA is positive, then that would mean ND is greater than NA, and this is actually our N side. When ND minus NA is negative, then this will be our P side. And we have defined the metallurgical junction to be where ND minus NA is equal to 0. Now, this is the plot of the doping profile. We will use this to, this also gives us the general shape of the charge density, rho as a function of x. So here we assume that we have some depletion with W, and at the x side, xn is equal to, at the n side, xn is equal to W over 2, and this side is minus xp is equal to minus W, sum minus W over 2. Now note that we came up that xn is equal to W over 2 and xp is equal to sum W over 2, and they are exactly the same, and that is because of the symmetry of the doping profile. So whatever, because of this symmetry, whatever depletion width we obtain, the two must be equal. We can use this. We also highlighted that outside the depletion region, the charge density must be 0, since the device must be charge neutral at that point. Now, the next step after obtaining the plot of rho of x is to get the electric field, and that is obtained with the Poisson's equation, where we related the derivative of the electric field with respect to x to the charge density over the permittivity of the semiconductor. So integrating rho of x will give us the electric field as a function of x. And since here we have 0, integrating 0 still gives us 0. Integrating some negative value will give us a negative area. Then integrating some positive value will make a rise in the total area being integrated until we go back to 0 since the area of this triangle must be equal to the area of this triangle. Now, since this is linear, then we end up with some quadratic function right here. And moving forward, we can plot the voltage as, or using this equation, E is equal to minus dV over dx. And so from the electric field, we still need to integrate it to get the voltage. So integrating 0, we define our 0 voltage here. Then this must be now some cubic function. This is cubic as well. And then this must be the total bending within the energy band diagram. So from this time, starting from a linear doping profile, we end up with a linear charge density, but only within the depletion region, quadratic electric field, and cubic plots of the voltage. Okay, let's start. So now we'll analyze PN junctions under some bias or some applied voltage. Here I've drawn the expected ID curve of the diode from the Shockley model, where this time we'll use the variable VA to denote the voltage across the diode. So this VA actually follows the same default notation where the positive terminal is at the P side. However, we'll consider only in our derivation voltage values that are less than VBI to ensure that low-level injection conditions exist to enable us to use the minority carrier diffusion equations. Now consider if, say, we have some positive diode voltage that we apply, then we expect some positive current ID to be entering our diode. But since that current has nowhere else to go, then that same current must flow within the device, throughout it, and until it goes out of the cathode. Now, in this lecture, we'll mostly talk about in terms of the current density, and we are assuming that the cross-sectional area of our device in consideration is constant, which means that if the cross-sectional area is constant and the current throughout is constant, then the current density across the device must also be constant. We'll just put into consideration the area factor at the end of the analysis. Now let's first have a review of the electrostatics of our PN junction diodes, starting with the equilibrium condition, where is also the case when we don't apply any voltage. So here we have the energy band diagram. This is the P side, and this is the N side, and we note that this EBD must be the one for equilibrium since the Fermi level is flat. We also see that even if the device is under equilibrium, there already exists some depletion region denoted by this W, which is the distance from this solid red line to the other edge right here. So all the solid red lines here represent the plot when it is in equilibrium. Also, within the depletion region, there exists some electric field, which is negative, so meaning it is directed from the end, from the right to the left, which is also depicted here by this downwards slope. So the slope actually indicates the electric field. We also integrated this electric field to come up with this voltage right here, and if we flip this, we actually get this shape right here. Now the built-in voltage is this voltage right here at thermal equilibrium, which is denoted here as QVBI, or the bending in the EC. Now let's consider if we apply some bias, starting with some forward bias, meaning VA is some positive value. The positive applied voltage or forward bias actually introduces an electric field that counteracts the initial built-in electric field. So if you notice here, the slope downwards is now more flat, meaning we get this smaller slope, or sorry, smaller electric field in this line. Also, you may have noticed that the depletion width actually shrinks when we forward bias the device, and that is actually depicted by this line here, where the depletion region is actually shorter. Now, if we look back, the um, we obtain this electric field by integrating this raw plot. So the integral now starts from here. So the plot of the electric field for this forward bias case starts from here, and we get this line right here, which relative to the first one, the solid red line, must have the same slope since we have this same constant value right here. So when we integrate that, we actually get the same slope, but this time it is actually moved towards to the right, this the start of this plot. So at this point, we also get the same slope since the height of this thing did not change, but we end up earlier. Now, in terms of the voltage, since the EBD became more flat, then this bending right here actually decreased by some amount, and that decrease is actually related to the applied voltage. Looking at the Fermi level, we know that the Fermi levels are not anymore flat since the device is not anymore in thermal equilibrium, and the difference between the Fermi levels at the two endpoints is actually proportional to the applied voltage. So QVA is the difference between the Fermi levels, and whatever change here happened actually also here. So now we indicate the bending right here as QVBI minus VA, which is which corresponds to this smaller plot right here. So this is QVBI minus VA, and therefore this must be the applied voltage. So note that VA here is positive, so we subtract something positive and we get something smaller. Note also that under this case, the Fermi level at the P side is lower than the Fermi level at the N side. So this is the plus terminal and this is the minus terminal. So this one is lower because the voltage is related to the energy band diagram by a negative proportion. So we flip this to get this, and therefore this being at a lower level actually means that this is at has some positive applied voltage to it relative to this one. Now for the reverse bias case, when VA is less than 0, we get this plot right here where we actually amplify the built-in electric field and make this bending steeper, and we get this stronger electric field right here. The depletion width also expanded, and so the plot for the reverse bias case is this plot here with a larger width. Now the bending became larger. Now how do we indicate this portion right here? So that actually still corresponds to QVBI minus VA, where this time VA is negative. So we subtract something negative, so we get this larger value. In terms of the Fermi level, this distance right here is QVA now downwards since VA is negative. Now this QVBI minus VA also applies to this one, although at this case VA is 0, so we just end up with QVBI. Okay, so now we present the equations that we'll need to be able to draw the energy band diagrams we have shown in the previous slide. So this time we'll consider a general case where the applied voltage is 0. So starting from the built-in potential, we know that the built-in potential is actually defined by the doping concentrations and the doping profile, and it actually does not change with bias, since the built-in potential is actually defined as the built-in voltage across the device when it is in equilibrium. So by definition, we will not consider the applied voltage in the formulation of the built-in potential, and so we can still use this same set of equations. So this is the, say, quote-unquote normal case, and this is the case when one side is so heavily doped that it is actually already degenerate, where the other side is non-degenerate. So from there we move forward. Now we um, try to come up with our modified equation for the depletion widths. So for some observations, first we noted that when we forward bias the device, the depletion width shrinks. When we widen when we reverse bias the diode, it actually widens the depletion width. And skipping the derivations, it can be shown that for step junction, abrupt p-n step junctions, um, we can simply add this minus VA term here for the depletion width. So this is actually consistent. When VA is greater than 0, we subtract something positive, so this one becomes smaller. When VA is less than 0, we subtract something negative, so this one becomes larger. And this, say, formulation can actually be extended for our xn and xp. So we simply added this minus VA terms. Now, when we get the ratio of xn and xp, it actually retains the ratio. So when we still had these equations when the device was in thermal equilibrium, although this also applies when the device is not in thermal equilibrium, again for step junctions. And why is that so? Consider this plot of the charge density. Say this is the equilibrium case. When we forward bias the device, the depletion region, or sorry, when we say we widen the depletion region, we're considering a reverse bias case, then um, the plot actually extends a little bit, and so we add this smaller area here. But since we must consider that the whole area on the n side and p side must be the same, then we add this smaller area here that corresponds to the new area on the other side. And so the ratio of these new areas must be the same as well to maintain the same area. So the ratio of the um, depletion widths on the N and P sides is actually maintained and is a function of the ratio of the um, a function of the doping concentrations. So these are the actually new equations that we'll use when um, the bias is not anymore 0. So in general, so what we observe here is that we simply add a minus VA term for every VBI we see in these expressions. So obviously the change appears in these two equations since there is no VBI in these equations. However, these equations actually changed as well, although that is not obvious since we don't have the VBI explicitly indicated here. But note that XP and XN also change with bias, and therefore they are functions of the built-in voltage. So XP is a function of VA, XN is a function of VA, and the total depletion width is also a function of VA. And so when we change VA, these terms these terms, this term, 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 all changes with bias, although not obvious in this formulation. Another note, at the metallurgical junction at x is equal to 0, we can actually compute the maximum electric field which happens at the metallurgical junction to be equal to 2 VBI minus VA over W. So note that we have this magnitude right here, and we actually obtained that from the plot of the electric field. So if you remember, the plot of the electric field looks like this one, Emax. And when we integrate that, we get this plot of voltage, where we expect that at the end point, this must be equal to VBI minus VA. However, that maximum portion is the maximum of the integral, and therefore the area of this triangle must be equal to this height right here. So if we get the area of the triangle, we'll have 1/2 base times height, where the base is W. So let me write here 1/2 base times height is equal to the area of the triangle, which we have just mentioned to be VBI minus VA. And so we end up with the equation below. So this one actually came from this one. Now this equation right here can also be derived from the same formulation right here. Now what if we say get the voltage at x is equal to 0? The voltage at x is equal to 0 is related to the area of this triangle right here, where the height is still equal to Emax, so 1/2 base times height, so the base is actually this time XP, and then the height is still Emax, and that is equal to the voltage at x is equal to 0. So the voltage at x is equal to 0, we can actually, the left side we can multiply by W over W. So here we observe that we still have that 1/2 W Emax, which we just said to be equal to VBI minus VA, but here we have the ratio of XP and W, which is this term right here. So now let's have a qualitative analysis of what does the bending in the EBD means with our current. So we start again with the equilibrium case when VA is equal to 0. So note that the Fermi level is flat. This is the N side with a lot of electrons, and this one is the P side with a lot of holes. So the electrons on top are decreasing, since electrons tend to stay at lower energy levels, whereas for holes, the lower energy levels are actually above or at the higher portion of the energy band diagram. Now, given this distribution, we know that carriers can drift and diffuse across the material, but this is balanced exactly such that there is no current for thermal equilibrium conditions to be achieved. So obviously the electron here will drift towards the other side as assisted by the electric field. The hole here will drift to the other side since the for drift, holes act like balloons, so they drift to the other side. However, since there are more electrons here, then they will diffuse leftwards. There are more holes here, so they will diffuse rightwards. And this drift diffusion scenario here actually cancels each other such that we achieve zero electron current and zero hole current. So there's no net current. However, when we apply, for example, say reverse bias, then the voltage is negative and the bending becomes more prominent. So what happens? So we have a steeper EBD, so a stronger electric field, and that still helps the electrons here to go and drift to the other side. However, the original carriers that were actually able to diffuse to the other side, this time will not be able to diffuse to the other side. And therefore, at this case, this drifting component actually dominates and will have a net current because of the carriers drifting across the depletion region. However, there is only few carriers that can drift. Remember that this is the p side, so there is only few electrons. This is the n side, so there are only a few holes. And let's say we make this thing more steeper, then the number of electrons that can drift will hardly change, and the electrons here will still not be able to diffuse, and that's why we actually get a current that is approximately not changing when we reverse bias our diode. So here. However, when we forward bias the diode, this time we apply a positive applied voltage, then the bending becomes less steep. And what happens? The carriers can still drift to the minority carriers can still drift to the other side. This small arrow here represents the original carriers that can diffuse to the other side. However, since the EBD is now more flat, then it actually becomes more easier for majority carriers to diffuse to the other side. And now it becomes obvious that the majority carriers diffusing to the other side becomes the net current component. And since the number or density of carriers that can diffuse actually exponentially increases as we make this more flat, since if you notice here, there are more carriers at the nearer EC for electrons and nearer EV for holes. So the more flat this energy band diagram is, the more carriers can diffuse to the other side, and that actually increases exponentially, or the cause of the exponentially increasing current. So the more forward bias, then more carriers can diffuse, and the larger the current. Let's take a closer look at how carriers interact with our forward biased step junction. So again, consider that a forward bias VA greater than 0 is applied, then the potential barrier to diffusion across the junction is reduced. So that makes the carriers from one side be able to diffuse easier to the other side. Now, in this case, we say that minority carriers are injected into the quasi-neutral region. So this is the depletion region, and the seemingly flat regions are the quasi-neutral region. So we say that minority carriers are injected into them, since as our carriers diffuse, say the electrons from here diffuse here, then they are now treated as minority carriers. So since this is the p side, electrons are injected into them, and therefore these new injected electrons are considered minority carriers. The same is true for holes at the injected into the n side. They are considered minority carriers at the quasi-neutral regions, which are the parts of the EBD that look flat and are outside the depletion region. Now, what happens after they diffuse into the other side? Now, we note that in this quasi-neutral region, there are now more excess minority electrons, so delta NP is greater than 0, and in this part, delta P sub n is greater than 0. And we know that when there are excess minority carriers, there are a lot of holes in this side, so the tendency is they will diffuse further, but recombine along the way. So here, there are more electrons here than there are electrons here. So they will still diffuse towards that direction, but they will recombine along the way. And the same is true here until they are, say, fully recombined. However, for the process to continue, say the electrons here recombined to some holes, so there are holes that are now missing from the point of view of this side, so that missing holes must be replenished. Okay, and at this portion, the missing electrons must also be replenished for the current to be sustained and achieve a steady state or DC value. Now let's look at the currents we can use to describe the current in our PN junction. We'll start with the general equations. So we just mentioned that we're assuming that the current density is constant throughout the device, and it has two components, the electron currents and the hole currents, which are both not necessarily constant and will take as a function of space. Now, these two currents have their own drift and diffusion components. So these equations can be used in general. Now, this equation we shifted from the derivative of n to the derivative of delta n, and from p to the derivative of delta p, since although these equations right here are only valid when n naught or p naught are constant, and which means that is only valid in our step junction at the quasi-neutral region, because here, even as the device is in thermal equilibrium, the equilibrium value actually varies in this portion. So we'll use only this for the quasi-neutral region. So again, we are considering that J is constant and not a function of space, but Jn and Jp may vary with position. Now, since we will actually eventually use MCDE in the quasi-neutral regions, and from our MCDE approach, we actually disregard these terms for the minority carriers. So more on that on the following slides. We just mentioned that we will use MCD in the quasi-neutral region. However, in the depletion region, what we'll actually use are the general continuity equations, and we'll actually assume that, or we will assume that at the depletion region, there is no light and that we have already achieved a steady state. So these are the this is the continuity equation, but we equated this to 0 since we are assuming steady state, and we remove the term for light. Now, further, we will also make a critical assumption for now that there is no thermal RG at the depletion region. We will consider the case that there is RG when we talk about non-idealities of the diode. But for now, let's accept that we are assuming that there is no RG. And what does that mean? If there is no RG in the depletion region, then these terms must be equal to 0. And what we are left is actually these two terms, which means that the derivative of Jn or Jp is equal to 0 at the depletion region. So if the derivative is 0, then Jp and Jn must be constant at the depletion region. So that's our simplification for the depletion region. Now let's look at the overview of what we will try to do to come up with the total current density and eventually the total current in the diode. So let's assume we have a forward biased diode. We said that electrons are injected at the p side and holes are injected at the n side, and they diffuse further into the other end and recombine along the way. So the electrons diffuse from this portion and get lower in concentration along the way and diffuse, and the same is true for holes. Now this diffusion at the quasi-neutral region due to the injection of the carriers will produce some diffusion current, which is the dominant minority carrier in the quasi-neutral region. And since electrons are diffusing to the left, then we expect to have a diffusion current to the right, which we will denote as the green plot here. Now the holes will diffuse to the right and produce a diffusion current to the right. Now this portion here is the quasi-neutral region, and we'll use NCDE to get the expressions for this one. So note that MCD is only for the minority carriers. So at the P side, we can obtain Jn, and at the N side, we can obtain Jp. Now we need boundary conditions to get the actual expression. So we'll use the law of the junction to get some boundary conditions. Next, what will we do after we perform MCDE at the quasi-neutral region? We go back to this assumption where we assume that there is no RG at the depletion region and that Jp and Jn must be constant within the depletion region, and therefore these values here we can evaluate that at the edge of the depletion region. So this is Jn at minus xp exactly, Jp at xn exactly, and we can assume that that is the same throughout the depletion region with this assumption. Now after that, we also said that the total current must be constant, and since at this portion we know the value of Jn and Jp, then we can simply add them. So we add this two here, and we already get the total current density at this portion. But we said that the total current density must be constant, and therefore we can extend that line throughout the device. So given that information that we know the total value, say at this point we know Jp, the red one, then we can simply subtract to get the green one. And with that, we'll be able to determine the current densities for both holes and electrons and the total current density throughout the diode given some bias. Now this one is drawn not equal. This actually depends on the doping concentrations. Okay, what are the assumptions, therefore, if we are to do the process we have just outlined? So we'll start with a non-degenerately doped step junction. It can be easily adjusted to consider that one side is degenerately doped. So we'll start with this general one, and we also assume steady state conditions so that we get the DC current, that low level injection conditions prevail in the quasi-neutral regions to enable us to use the MCDE, and that the RG in the depletion region is negligible so that we end up that Jn and Jp are constant in the depletion region. So using those assumptions, we will solve the MCDE at the quasi-neutral regions to get some function of the excess carrier concentrations as a function of both space and the applied voltage. We'll apply these boundary conditions. So we have some value of the excess minority electrons at the edge of the depletion region, and also for the minority holes at the edge of the depletion region at the end side. However, far from the depletion region, um, we'll also need some value for that so that we can solve the constants later on. So delta NP at minus infinity and delta P sub n at infinity. Also, we'll have to determine with this, we'll be able to determine the minority carrier current densities in the quasi-neutral region. So since actually MCDE gives us a function of delta N and delta P, now we'll use the function of delta N and delta P to get the Jn and Jp. So that enables us to get the plot we have a while ago that looks like this one. Okay, so that are the two functions right here. So we'll use the expressions for delta np and delta pn to get the function for jn of x and jp of x at the quasi-neutral regions, which are outside. So these are minority carrier currents. So this is jn at the p side and jp at the n side. So once we get that function, following the procedure we have highlighted, we'll get their values at the edges. So Jn at minus xp. So that is this term. And we'll add that to the value of Jp at xn. So that is that term, which enables us to get the total current J, which is not anymore a function of position. So once we get the total J, then we can actually equate that to the, say, the total current, and that should be equal to the current in our Shockley diode equations. So to do that, we'll look at more details. So first, consider the equilibrium carrier concentrations. So since we are talking about equilibrium, that is VA is equal to 0, carrier concentrations, that so this actually refers to N and P. And since this portion we're talking about XP and XN is at the edge of the quasi-neutral region, then when we apply no voltage or at thermal equilibrium, the values of the carrier concentrations at the quasi-neutral regions look like our usual expressions. So at the P side, the whole majority concentration is approximately Na at that portion, and the minority carrier concentration at the P side is simply Ni squared over Na at the edge of the quasi-neutral region, or at the edge, which is also the edge of the depletion region. For the n side, we get this simple expression that the majority carrier is simply um, Nd, whereas the minority carrier is Ni squared over Nd. So plotting that, actually, let's say we have Na is greater than Nd, and so say this is X, and we have the depletion region right here at thermal equilibrium. Since Na is greater than Nd, then this should be P sub P, and this should be N sub N. So if we use Ni squared over Na is large, so we get some small value of N sub P. For the other side, we get this minority carrier concentration P sub N. Now, this P sub P naught at minus XP is actually this one here. N sub N naught at Xn is this one. NP naught at minus XP is this one. And P sub N at Xn is this one. Now, if low-level injection conditions prevail in the quasi-neutral regions when we apply some voltage, non-zero voltage, then since this is low-level injection, then the majority carrier concentrations should not actually vary that much from their equilibrium values. Okay, however, the same cannot be said for the minority carriers. Since we are assuming LLI conditions prevail in the quasi-neutral region and at these portions, then we can draw two quasi-Fermi levels at the quasi-neutral region, the quasi-Fermi levels referring to the majority carriers. So say we have this step junction diode where we expect the equilibrium Fermi level to be at this level relative to EI at the P side, and at this level relative to EI at the N side. Since for LLI, majority carrier concentrations are not perturbed significantly, then we expect that Fn, the quasi-Fermi level for the N side, and that is not exactly EFN, is at this level. Now, for the other side, we say that Fp must be around this portion right here. Now, the law of the junction assumption states that the voltage VA applied to a PN junction falls mostly across the depletion region. Now, what does that mean? We can actually visualize that with this diagram where we extend the quasi-Fermi levels across the depletion region, and the difference must be exactly equal to or to the applied voltage VA with a factor Q. Now, what makes this assumption plausible is that, if you may recall, the depletion region is a region where there is almost no carrier or very small carrier concentration, meaning this portion has a very high resistance relative to the two quasi-neutral regions, that if we apply a voltage across the two ends, most of the voltage will fall mostly across this region. Now, again, we're using the law of the junction to get a boundary condition for the minority carrier concentrations at the edge of the quasi-neutral region. Now, if you focus at this side, since we put Fn at this portion, then we can actually compute N at the P side with some applied voltage, and at the N side, we can compute P using this quasi-Fermi level Fp. Now, in general, we can set up some equation at this whole depletion region at the middle. Note that we have these general equations for P and N. So P is simply Ni e raised to Ei minus Fp over Kt, using the quasi-Fermi level for P, and N is equal to Ni e raised to Fn minus Ei over Kt, where Fn is the quasi-Fermi level for N. Now, notice that if we multiply the two equations, we get Np is equal to Ni squared e raised to this, Ei minus Fp over Kt, times this, which means we can add the two exponents, Ei cancels out, and we're left with Fn minus Fp. Now, Fn minus Fp is exactly equal to QVA. So since Fn minus Fp is equal exactly to QVA at this portion, then we can have this law of the junction formula for the depletion region. Now, how do we use this? For example, we have the N side. We know that at this portion, N is approximately equal to Nd. Then we can simply compute for P as Ni squared over Nd times e raised to QVA over Kt. At the other side, we can solve for N by knowing that P at this portion is approximately Na, and therefore N is approximately Ni squared EQVA over Kt over Na. So again, at the edges of the depletion region, where the quasi-neutral region starts, we are assuming low-level injection such that the majority carriers are not perturbed significantly. Now, using the law of the junction, we have just shown that at the edges, the minority concentrations can be computed as Ni squared times e raised to QVA over the doping concentration at that side. So for the minority electrons at the P side, this term here is simply Np naught, or the equilibrium value, times E raised to QVA over Kt, and the same format can be obtained for Pn, which is the minority whole concentration at the N side. Now note how this actually makes more sense. If we consider Va is equal to 0, then we simply end up that Np is equal to Np naught, since e raised to 0 is simply 1. Now we go back to the case where we apply some voltage, and we actually now can simplify the expression as using this format. The excess carrier concentration is the actual carrier concentration minus the equilibrium value. So we subtract this one with Np naught, and we get this equation. So Ni squared over Na e raised to QVA over Kt is equal to Np, while Np naught is simply equal to Ni squared over Na. And this same format can be obtained for the excess hole concentration at the N side, so the excess minority carrier concentration. Now, these two values again are important for us, and we'll use them as the boundary conditions for our MCDE. Some example first. Consider we have a silicon PN step junction with these doping concentrations, and we apply some voltage 0.6. What are the minority carrier concentrations at the depletion region edges? Now, before proceeding, let's draw the carrier concentrations at equilibrium. So voltage is equal to 0. So at equilibrium, we have Pp naught, Nn naught, Np naught, Pn naught. The value of the majority carrier concentrations are 10 to the 18 and 10 to the 16. And we have Np naught to be 10 to the 2 and Pn naught to be 10 to the 4. Now going back to the problem, we apply some forward bias 0.6. So with some forward bias 0.6 volts, we expect that we are injecting majority carriers at the other side. So meaning the minority carrier concentrations are larger at the edges and recombine along the way. So equation-wise, how do we represent the minority carrier concentration at the edges? So note that these are minority carrier concentration. So we're talking about some N sub P and P sub N. But since it is mentioned here at the depletion region edges, then we are actually referring to the values here. Okay, and that must be NP at minus XP and P sub N at XN. From our law of the junction, we have shown that the minority carrier concentration is simply equal to its equilibrium value multiplied by e to the q VA over KT. So NP naught is equal to 100 times e raised to 0.6 over 0.026, and we end up with this is 10 to the 12. Now for the other one, Pn naught is 10 to the 4 e raised to 0.6 over 0.026, and this gives us 10 to the 14. Now note that we went from 10 to the 2 to 10 to the 12. We multiply by a factor of 10 raised to 10, and that must be represented by this one. And since we are multiplying the same factor to P sub N, then we just went from 10 to the 4 to 10 to the 14. So we can actually, if we know the ratio of the equilibrium concentration and the actual concentration at the edge with some applied voltage, that same ratio should appear at the other side. Now next, say we are asked what are the excess and minority carrier concentrations. So excess minority, so we are actually being asked what are delta N sub P and delta P sub N still at the edges, although it was not anymore mentioned here. So the excess is simply the actual concentration minus the equilibrium concentration. So 10 to the 12 minus 10 to the 2 is approximately 10 to the 12, and 10 to the 14 minus 10 to the 4 is approximately 10 to the 14. Going back to our derivation, we are now actually ready to proceed with the minority carrier diffusion equation. So this is the simplified form when there is steady state and no light at the end side. So again, this is for minority carrier, so we are dealing with holes at the end side, for example. So just a quick recap. So we have this MCDE for holes at some N-type material, and at steady state, we equate this to 0, and at no light, we equate this to 0. So we can simplify this equation to be equal to this one, where we just transferred this to the other side and divided by dP. Now, dP tau p is equal to simply Lp squared. Now, for this one, we actually get some second derivative is equal to the same function. So we get the two exponential general solutions, and we need two boundary conditions. So we use these two using the law of the junction. So we take the excess minority hole concentration, which is Pn naught e raised to QVA over KT minus 1. So when there is delta, we have this minus 1 to subtract from the thermal equilibrium value. However, far from the quasi-neutral or far from the junction, we assume that the excess minority carrier simply die out to 0. And we will also introduce a new coordinate system to aid us in our analysis, since having x is equal to 0 at this portion will be a bit hard if we are considering only the quasi-neutral region for the MCDE. So this time we'll define x prime to be 0 starting at x is equal to xp, going in and increasing as we go into the quasi-neutral region at the n side. For the p side, we'll introduce x double prime, which is 0 at x is equal to minus xp. However, this time this is increasing at as we go leftward. So with this new coordinate system, we can simply use our general solutions from our continuity equations lecture without much change. So again, the general solution for this one is of this form, and we'll use these boundary conditions to solve the equation. Now we start with this general solution, although note that we are using the axis x prime for the whole concentration at the quasi-neutral region at the n side. Now applying our two boundary conditions, we will actually get these two solutions right here. So if they exist as x approaches infinity is 0, then therefore this exponentially increasing term must be non-existent. So this must be not here. So a1 is equal to 0. And we therefore are left with equating Pn naught eqva over kt minus 1 at this side is equal to a2 times e raised to minus x prime over lp. And when we evaluate that at xn, which is actually x prime is equal to 0, then we'll be left with Pn naught e raised to qva over kt minus 1 is equal to a2 times e raised to 0. So we'll just get a2 as simply equal to this one. And therefore, substituting the constants we obtained, our function therefore is simply a2 e raised to minus x prime over lp, or Pn naught e raised to qva over kt minus 1 times e raised to minus x prime over lp for x prime greater than or equal to 0, or simply x greater than or equal to xn. We can follow the same approach, this time in terms of x double prime for the holes at the quasi-neutral region at the p side, and end up with the same similar expression. We simply change Pn naught to Np naught, and from x prime, x double prime, and from Lp to Ln, and which is valid for x double prime is greater than or equal to 0, or x is less than or equal to minus xp, since we are considering this side. Now here we show how we can normally plot the carrier concentration profiles under some forward bias. Now assuming we are given the carrier concentrations on the two sides of our step PN junction, then the first thing we can plot is the majority carrier concentration at the two sides. So P sub P is approximately equal to Na, and N sub N is approximately equal to Nd, and assuming that LLI conditions prevail, then even under forward bias, these majority carriers should still be approximately equal to these values. The next thing we can actually plot is the equilibrium value of the minority carrier concentrations using Ni squared over Na and Ni squared over Nd. However, this will just sort of act as our guide, since these are not the actual values, as we are applying some voltage. Now, if we apply some forward bias, then we can compute the carrier concentrations at the edge, minority carrier concentrations at the edge of the depletion region using the law of the junction. So for example, this P sub n is equal to, so P is equal to Ni squared EQVA over KT over N, which is N naught or ND. So we can get these two values, and using our previous result, that we have this expression. So first, delta NP at x double prime. So at the P side, x double prime is some initial value, but is exponentially decreasing as you go along x double prime, so leftwards, based on this tau, which is ln. So on the other side, at the n side, we refer to x prime, we have some starting value for the excess carrier concentration, and that excess exponentially dies out as we go along x prime. So we can actually plot that as this linearly looking plots, since this is an exponential function with respect to x, but we are plotting the logarithm, so this actually looks linear. However, note that this function gives us the excess and not the actual concentration. So looking at the far ends, when x prime approaches infinity, so that is at this portion, e raised to minus infinity is 0. So the excess is 0, and we end up with the thermal equilibrium value. And the same is true at this portion. Okay, so we can use the law of the junction to determine the actual minority carrier concentration, or we can use this plot or this function, evaluate it at, say, x prime is equal to 0, then add it to Pn naught to get Pn. Now, for the reverse bias case, this time there will be a depletion of minority carriers at the edge of the depletion region. Instead of having some excess, there is actually a deficit of minority carriers at the edge of the depletion region. So inspecting this further, at the edge of the depletion region means at x prime is equal to 0, or at the other side, x double prime is equal to 0, meaning if we simplify these two plots, then this term actually turns out to be equal to 1 at x double prime is equal to 0, and this simplifies to 1 as this one is evaluated at 0. However, we are considering here a reverse bias, so meaning VA is some negative value, and if that negative value turns out to be high enough in magnitude, or this exponential is negative enough, then e raised to something negative can be considered very small as compared to this negative one. So this one can approach 0. So approximately, with enough reverse bias, then this should simply end up with, so this one is approximately 0, or rather this whole term here is approximately equal to -1, and therefore the excess minority carrier concentration must therefore be approximately equal to minus NP naught at the edge. And this one is approximately minus Pn naught at the edge, meaning if we get the actual N or P, N is equal to N naught plus delta N, and therefore at the edge, N at x, N at, say, x double prime is equal to 0 is equal to N naught, which is a constant, plus this value right here, which is minus NP naught. And therefore, we end up that this value is approximately equal to 0. That's why we used a linear plot, since we cannot actually draw properly 0 using a logarithmic plot. Now, this also tells us that the only current that flows due to drift um, is due to drift of minority carriers across the junction. So remember, when we reverse bias the junction, minority carriers drift within the depletion region, and that drifting minority carriers is supplied by the diffusion that happens here. So now that there are fewer electrons at this portion, and so electrons will diffuse from this part to this part, and once they get at the depletion region, they will start drifting. And the same is true for holes. The holes drift from the p side, from the n side to the p side, and that is supplied by this one. So there are more holes here than here, so holes diffuse towards this portion, and once they get at this portion, they will drift to the other side. So this drifting current is fed by the diffusion of minority carriers towards the junction, which is supplied by thermal generation. And that is because, as there are only there is a deficit of carriers, then generation will actually be the dominant RG force in this section. So as they are drifted to the other end, new carriers are being generated to maintain steady state. So given that we already have a function of delta NP of x double prime and Pn of x prime, we can then proceed and derive the minority carrier current densities at the p side and the n side. So at the p side, we know we will now derive Jn. At the n side, we will derive Jp. So this delta Np at x double prime is actually equal to this function right here, and performing the derivative, so we end up with qdn times, this one is a factor, not a function of x, so we copy that, e raised to minus x double prime over ln, and by chain rule times minus 1 over ln. So the negative by chain rule actually canceled the negative here. We can do the same for the n side and get this expression right here. So what can we observe? So this tells us that at the p side, we have some starting current that is exponentially decreasing as we go deeper into the quasi-neutral region at the p side. So that is depicted by this plot, and we are now actually able to obtain the expression for these two plots. Now we proceed with the analysis, and we have said that the total current is simply the sum of Jn at x is equal to minus xp, which is this one, and of the current Jp at x is equal to xn, which is this one. So we add them to be able to obtain the total current J. So in terms of our new coordinate system, at x at minus xp is x double prime is equal to 0, and x prime and x is equal to xn is x prime is equal to 0. And therefore, we just need to evaluate the two equations at x is equal to 0, and that should give us that e raised to minus 0 is simply 1. So we disregard this term, and simply add these two. So we have a common factor EQVA over KT minus 1 and a common factor Q Ni squared. Okay, so we expand this to Ni squared over N, Na, this one is Ni squared over Nd, factor out Ni squared, and we actually get this one, which is now very similar to our Shockley equation. Although this time we are writing it as in terms of current density. So to be able to obtain the expression for current, we simply multiply the current density by A, and comparing the form of the equation, then we can actually say that I naught is equal to this expression right here. So we now have an expression for the reverse saturation current, and that is A Qni squared times dN over ln Na plus dP over Lp Nd. And plotting that actually gives us this solid line right here. Although if we compare that with actual measurements, the circles, this actually tells us that the expression, the Shockley model, does not actually capture perfectly what's happening within our device. Although for now we're still okay with this expression, and we'll further inspect what this means. So the diode saturation current is again this expression right here, where we can say that this I naught actually can vary by orders of magnitude depending on the semiconductor material, because of this Ni squared term here, which varies per material, and also this doping concentration term right here. Now, for an asymmetrically doped PN junction or a one-sided junction, the term associated with the more heavily doped side is negligible. So if Na is much greater than Nd, then we can simply remove this term right here and end up with I naught is approximately AQNi squared dP over LPNd, and for Nd much greater than Na, we can disregard this term and end up with this one, which again means that I naught is determined by the lightly doped side, since the term for the heavily doped side is negligible. Now let's just be careful in interpreting this equation right here. So dN right here is the diffusivity of electrons at the p side. Okay, so the subscript is N, but that actually refers to the diffusivity of minority carriers at the p side. And this Ln right here, by definition, L is the minority carrier diffusion length. So this is the diffusion length of the electrons at the p side. And these terms are partnered with the doping concentration at the p side. So all of these terms actually refer to the p side. All of these terms refer to the n side. So in summary, the total voltage dropped across a PN junction is equal to VBI minus VA. And that is seen at the voltage plot, or at the EBD, where the bending is QVBI minus VA. And we skipped the derivation, although we said that the depletion width is now equal to this expression, where we just included this minus VA term. Since going back, the derivation actually referred to, or needed, the value at the voltage at this portion, although that voltage now became VBI minus VA instead of VBI. So we simply changed this term to VBI minus VA. The electric field can also be shown to be equal to this one, which tells us that um, if we apply a reverse bias, a negative VA, then the peak electric field actually strengthens. Okay, and reverse bias strengthens the electric field. A forward bias weakens the built-in electric field. Under forward bias, the potential barrier to diffusion is reduced since we are flattening the EBD, and it is easier for majority carriers to diffuse to the other side and get injected into the quasi-neutral regions where they start diffusing towards the other end. Now, the law of the junction gave us this equation, which is applicable for the depletion region, which enabled us to have an expression for the minority carrier concentration at the edge of the depletion region or at the start of the quasi-neutral region, which we use to derive the diode current. So this is our new equation, which is similar in form to the Shockley equation, where the reverse saturation current is AQNI squared dN over ln over NA plus dP over LP ND, which again tells us that the property of the diode is again dictated mostly by the lightly doped side. So that's it for this lecture. Thank you very much.